Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on the efficiency of three-phase induction motor in the losses and efficiency determination. Now first, what is meant by efficiency? Efficiency means the ratio of output to the input is known as the efficiency. Percentage efficiency equals to output by input into 100. This is percentage efficiency. Now in case of induction motor, whatever the machine, the efficiency equals to ratio of output to the input. That is okay. Now in case of induction motor output is mechanical energy and electrical energy is input is the three-phase supply. Now here electrical energy is the electrical energy is the input, electrical input power this one, and mechanical output power this one. Now efficiency, percentage efficiency equals to mechanical power output divided by electrical power input into 100. Now here if you give electrical input to this three-phase induction motor, so now here you will get mechanical output, mechanical power output plus you will get some losses. So now what is the equation here? If you give input to any machine, you will get output and you will get total losses. Here losses in the machine, here different losses are here, constant losses and variable losses. Here in case of induction motor, different losses, stator copper losses, stator iron losses, rotor copper losses, rotor iron losses, and it is a rotating machine means there are maybe windage losses. Next, frictional losses. Now here efficiency equals to output by input. Here input equals to output plus some losses into 100. Now here efficiency equals to mechanical power. Here it is the output is a mechanical power, and that is output and mechanical power output plus losses are divided into constant losses plus copper losses. Here copper losses means constant losses means copper losses are variable losses here. Here this total losses, these are the losses, this one is the output and this one is the output. So now efficiency equals to output by input, input equals to output plus losses. Here losses are constant losses and variable losses. Now efficiency equals to this one, P mechanical divided by P mechanical plus P constant losses plus P variable losses. Now into 100. Now what are the losses here? Here the losses here, the power flow diagram for three-phase induction motor. So first this is the three-phase induction motor. This is RYB three-phase induction motor. Now if you give, this is the supply, three-phase supply, RYB three-phase supply. Now electrical power input to the stator. This is the stator of the induction motor. Now electrical main purpose, it will convert from electrical energy to the mechanical energy at the shaft. So here electrical energy as the input and mechanical energy as the output at the shaft. If you give 100% of electrical energy, here you will get the 88% of mechanical power. So remaining 100 minus 88.5, that means 11.5 are the losses here. Input equals to output plus some losses. Here 88.5 plus 11.5 are, here 11.5 are losses. So what are the losses in the three-phase induction motor? So first loss here, if you give three-phase supply to induction motor. So what here, there is a stator. So this three-phase supply is given to the stator winding. So what will happen? There is a stator winding, this stator having core. So core having some losses, core losses, stator core losses. That means stator iron losses. Stator iron losses are stator core losses. These losses are 2.5% here. Now here this stator core carries some some winding here, three-phase winding. That winding is star connection winding. That winding is star connection winding. So because of this winding, when current flows, when you give the balanced three-phase supply to three-phase stator winding, current flows in this winding. So that currents and that winding resistance provides the losses. That losses are known as, that winding is made up of with copper. That losses are stator copper losses here. Here actually the given supply, this is three-phase supply formula here. This is 100% and 3 into power formula. This is V1 into I1 into cos phi. Cos phi is a power factor, and this is 3 into 5. Total supply formula here 3 into V1 into I1 into cos phi. Now here stator copper losses formula is here 3I1 square into R1. So this stator copper losses percentage here in the losses percentage is 3.5 percentage, and stator core losses percentage is 2.5. And now this supply here, now remaining out of 100%, next to 7.5 and 2.5, 3.5 and 2.5, this is 6% here. Over 6% losses are stator losses here. These are total combination of these two addition. If you add the stator copper losses and stator iron losses, core losses, that means 6% losses are in the stator only. Now that power, this here RMF will be generated, rotating magnetic field will be generated, and it cuts the rotor conductors. So now that energy, this power transferred across the air gap to the rotor input. So rotor input formula here, I1 indicates the 1, here 1 suffix indicates the stator and 2 suffix indicates the rotor here. Now this rotor power input formula 3 into I2 into E2 into cos phi. This one 2 indicates the rotor and 1 suffix 1 indicates the stator here. Now here we have stator copper losses and stator core losses also. So rotor copper losses and rotor core losses. And rotor core losses are again divided into here eddy current losses and hysteresis losses. And this eddy current losses and hysteresis losses depending upon the frequency only, as compared to the stator frequency. This rotor frequency value is very less. So now we can neglect this rotor copper losses, means eddy current losses and hysteresis losses. Only we will consider this one, that may be 0.01 percentage only. So no need to consider this rotor copper core losses here. Rotor having winding, that winding having some copper material, so that because of that resistance and rotor current there may be loss. That loss is here 3.5 percentage. Now 6 this is 6 plus 3.5. Next this is 9.5 percentage here, and next this is at the shaft, and this is mechanical power developed in the rotor only. Now this is at the shaft, this is at the rotor, mechanical power is developed here. RMF cuts the rotor conductor and EMF will be developed in the rotor conductor, and there is a closed path, current flows in that rotor bars, and it set up the flux, and that flux and this rotating magnetic field, because of the Faraday's law of electromagnetic induction, and torque will be generated, mechanical energy will be developed. So that mechanical power developed in the rotor conductors only. Now here, because of this friction and windage losses here, so that percentage is 2. So here frictional losses and windage losses 2, 9.5 plus 2, that equals 11.5. So total losses in the 3-phase induction motor are 11.5. Now here this, if you add these losses, and here this is the power available at the shaft only, we will consider that is final output. Mechanical power output at the shaft and electrical power input to the stator. So these are the different losses here. Now here these losses are divided into 2 parts. iron losses, constant losses, and copper variable losses. Now next, constant losses plus variable losses. Now here next, if you give motor input to the stator of the winding, so here you will get stator copper losses and stator iron losses, and input to the rotor, and next, this, if you give input to the rotor, there may be rotor copper losses and rotor iron losses. Rotor iron losses are negligible, and there may be a mechanical power developed at the rotor. So now, because of this one, windage losses and frictional losses and mechanical total output power. This is at shaft, at the shaft only. Now here, different types of losses. So now here these losses are divided into, here we have different types: stator copper losses, stator iron losses, rotor copper losses, rotor iron losses, and windage losses and frictional losses. These losses are occur in two categories: constant losses and fixed losses. It will not vary. And next, variable losses. First I will explain variable losses. Different these losses are when current flowing through the stator and rotor winding. Stator. So current, this is a three-phase winding, induction motor RYB. So this three-phase stator carries the winding. So that winding, because of that winding and current here, so there may be a loss, that is stator winding, and rotor is also having winding, that rotor winding. Because of that rotor winding and current, there may be a loss, that is the rotor winding current. Now here next, load changes. If load changes, current changes, and rotor stator currents also changes. Now because of this reason, we will call this rotor copper losses and stator copper losses are variable losses. Next, stator constant losses. Here constant losses are fixed losses. These are considered. So there are two types of losses here further: iron losses, mechanical losses, and brush friction losses. Now first, iron losses. Here iron losses and another name is core losses. So these core losses are divided into eddy current losses and hysteresis losses. So core losses occur in the core only. Now here, first, hysteresis losses occur because of the reversal of the magnetism. So now here these losses, to reduce this hysteresis losses, also occur in the core because of the residual magnetism, and these losses are minimized by the using material. The core material is silicon steel, that is high grade material. Now if you see the formula here, hysteresis loss formula here equals to KHB maximum 1 power 6 F into V. V is the volume of the material, and F is the frequency, and B is the flux density, and KH is a constant. Next, coming to the eddy current losses. Eddy current losses are because of the eddy currents, means eddy currents are because of interaction of conductor and magnetic field here. Now here this eddy current formula, KE is a constant, and B maximum is a flux density, and F is a frequency, is a T is the thickness of lamination here, and V is the volume of the core. And here KE B maximum square F square T square into V. Now here if you see these losses are minimized by using laminated core. That laminated thickness here, T is the thickness. And next, laminating core, and this area decreases and hence resistance increases, that results in the eddy currents decreases. And next, these losses are depending on the frequency. And next, eddy currents and this rotor copper losses are less because rotor core losses. We are neglecting rotor core losses. Here, that this is the stator frequency S into FR. Sorry, this FR is the stator rotor frequency, and this is the stator frequency. The slip value is always 0.01 to 0.005. Now here, so as compared to the stator frequency, and this rotor frequency is very less, so we will neglect this rotor copper losses. And next, If suppose stator frequency, this is a 50 hertz and this is a 0.03 percentage and this value is 1.5 hertz as compared to the rotor stator frequency. Rotor frequency is very less and this is 1.5 and this is a 50 hertz. So now we can neglect this rotor. This is if you substitute this 1.5, this is a negligible value eddy current loss, and for that hysteresis loss also, that is also negligible value. If you add that eddy current loss and hysteresis loss, you will get the negligible core loss. And next here, rotor core losses are very small as compared to the stator core losses, and you can neglect under running condition. And next here, mechanical losses. So mechanical losses and brush frictional losses, these are also comes under the constant losses, and these losses occur at the bearings, and brush friction loss occurs in the wound rotor induction motor. These losses occurs in the wound, this is important, slip ring induction motor only, not in the squirrel cage induction motor. There are no brushes and bearings. In that case, only these losses are mechanical losses occur in the wound rotor induction motor or slip ring induction motor, not in squirrel cage induction motor. These losses are zero at the starting course. If you increase the speed, then these losses will increases. These losses are constant remains in the three-phase induction motor if speed constant. So these losses are constant because here three-phase induction motor speed is constant here. Now here, so what are the losses here? Losses representation here. So three-phase supply is given to the, this is the three-phase induction motor R, Y and B. So three-phase supply is given to the R, Y, B supply is given to this one, and stator of the three-phase induction motor. This is the first point. And next, now here this is the P input. In that, this V1 means this is the power, electrical power supplied to the three-phase induction motor, this one. And this is represented with P in this one, and this supply voltage, that line voltage, that is a line voltage supplied to the three-phase stator of the three-phase induction motor. And IL is a line current here. IL is a line current. And next, cos phi. Cos phi is the power factor of the three-phase induction motor. This power factor of the three-phase induction motor. Now here, total electrical power equals P input root 3 VL IL cos phi. This is V1 I1 here 3 only. Here if you convert into the phase voltage and root 3 into V phase, that value is 3 into V1 I1 cos phi. Here V1 and I1 are phase voltages and VL IL are here line voltage and line current here. Apart from this, input power is used to supply stator losses, and there may be iron losses are here, iron losses and stator copper losses here. Now these are stator copper losses and stator iron losses. Now remaining part here, that electrical power input, this input minus these two losses, stator losses. Stator losses are divided into two parts, stator iron losses and stator copper losses, that are supplied to the as a input. So now that value equals, this is represented with P2. So this representation is most important, and this P2 equals to rotor input equals to P in minus, these are the stator copper losses and stator iron losses. Stator losses, these are the stator losses. Okay, now P in minus stator losses. If you subtract from the P input to from the, and next stator copper losses, this one. Next, this is the P in and this is the P2, stator copper losses, stator losses only, stator copper losses plus stator iron losses. Now this rotor has to convert this rotor input to the mechanical energy. So now same way here, if you give the three-phase supply to the rotor stator of the three-phase induction motor, and rotating magnetic field will be produced, and according to the Faraday's law of electromagnetic induction, rotor cuts the RMF cuts the rotor conductors, and induced EMF will be developed. That induced EMF, the setups, there is a current because of the closed circuit. That current sets the flux, and that flux and RMF interacts, and that mechanical energy will be developed. So mechanical energy, rotor input to the mechanical energy, but this complete input cannot be converted into the mechanical output. So there are some rotor losses. Here rotor, these are the stator copper losses and stator iron losses, but here we are considering only rotor copper losses, not rotor core losses. Here rotor losses are two types: rotor iron losses, that means core losses, and rotor copper losses. These are negligible. I already discussed in the previous slide. And these rotor losses, depending upon the frequency, that is less 1.5 Hz less there, which is very small when rotor rotates. It rotates when induction motor is under the running condition. Now next, rotor has to supply. Rotor has only, this is negligible value, this one. So don't consider this rotor iron losses. So now here it has only rotor copper losses. This is the PC, and this rotor input has to supply the rotor copper losses. These are represented with PC only. Now here this one. After supplying the rotor copper losses, so the remaining part of the rotor input P2 is converted into this is the P mechanical energy at the rotor only. Now here these are the parts. PC is the rotor copper losses, and R2, here suffix 2 indicates the rotor, and I2B is the rotor current under the running condition, and R2 is the rotor resistance. And next, PM is the gross mechanical power developed. So this is the gross mechanical power developed, and this is the shaft power. And next, PC equals to 3I2 square, 3I2 square and R2 square. This is R2 square. And this power equals to PM minus PC is known as the, this P2 minus this one is known as the PM. Next, mechanical power developed in the rotor equals to P mechanical equals to, now this is the P input, and this one is the P2, and this is the P rotor copper losses PC, and this is the PM. So this is the mechanical power developed in the rotor. So this equals to rotor input to the power input to the rotor minus this PC rotor copper losses. And next, this formula equals to power input to the rotor, and this rotor copper losses equals to slip into power input to the rotor. This formula is important. And next, here the common value is 1 minus power input to the rotor only. Now here power input to the rotor and mechanical power developed by the rotor P input, and this is a P2, and this is a P in, and this one is the rotor copper losses PC. Now here next formula. So this is as it is, and this one is the, this one equals to this one, and this one equals to rotor copper losses equals to S. Power input to the rotor, and next mechanical power developed by the rotor and power input to the rotor. So rotor copper losses here. Now here the common power input to the rotor, power input to the rotor, power input to the rotor. This is 1 minus 1 minus S and S. This S indicates the here slip. Now final one. So efficiency is defined as the ratio of output to the input, output by input into 100. That one. Efficiency is represented with eta, and the ratio of efficiency of three-phase induction motor, rotor output by rotor. This is only for rotor only, not for entire machine. Rotor output and rotor input. This is the PM divided by P2 only. Gross mechanical power developed by rotor input, PM divided by P2 only. And this is represented with PM divided by P input. Next, three-phase induction motor efficiency equals to power developed at the shaft, not PM also. Here power developed at the rotor is different, power developed at the rotor shaft is different. Here mechanical and frictional losses will be added to this one, P output, and electrical power input, that is P input. Now I hope all these things are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.